that one. So, all right. Welcome, my friends. This is class number 2. So basically, yeah, this is kind of my PowerPointy style of things of when I have stuff up. But like I kind of said last time, I'm not gonna this isn't a class on using PowerPoint. PowerPoint happens to be kind of a good visual tool. It's better than me just watching my talking head flap at you. Normally in real life, I like to have like me in front of this, and I would be talking to you in real life. But we have to make little concessions with this thing. So I'm going to do my darndest to make this not boring, and also do my darndest to not go too fast. Like I kind of mentioned last time, I like my caffeine, so I tend to move a little bit fast. But good news is everything's recorded, and I do post everything. So if you ever need to go back for a quick explanation on it, you can just jump back onto the post, or just up to Canvas, and I'll have all the videos posted. Now, that one took me a little while. I didn't get it posted till last night for the 2 days ago, because it was like I'm using the school software version for recording the audio, or recording the videos. And I don't know, I prefer YouTube, but I'm trying to follow in line with the university policies. So using this, the TechSmith stuff, you might have to log in the first time to see it. But the cool thing is once you log in the first time with your school credentials, then it won't, from the rest of the semester, as long as you're on the same computer, it won't ask you for your credentials every single time. Because I find that really annoying if you have to enter all your passwords in every time. But it's just the first time you have to do that. But the cool thing is you'll have the reference there, and it's up there for you for if you need to look back on anything. So, yeah, I guess... normally I'll have announcements going on right here. So I start off each class with announcements, like what's going on, if there's anything new. There isn't really anything new. Well, actually, except for one probably, is that we have, quizzes. We have the first homework, which is supposed to be due. Let's see. I might have the date wrong on this one, but I'll make this one live. Let's change the calendar on this. It's from a week today. And I'll get this one actually published. This is something I meant to do before class. This is what it looks like behind the scenes for doing. Come on. Computer's being a little laggy today. It's today, 21st. Okay. So, the first homework, 28th. Save and publish. Just went live. So you have your first homework due a week from today. It's not very many questions. It's 22 points, but if we look at the preview on this thing, it's not too bad. So there's 11 questions, and you just kind of blast through this thing. Some homeworks will take more than others, but in the beginning of the semester here, the homeworks aren't necessarily meant to be brutally difficult. They're more meant to be, are you keeping up with the class? Are you keeping up with the reading? And are you staying engaged? And they're literally this homework will probably take you 5-10 minutes at best. They will ramp up and they will get more difficult going forward, but this just to kind of get you in the speed in the flow. This is just kind of how it rolls. So it's not too bad. But it is due a week from today. And so the way it works is that homeworks are going to go live every Thursday, and they're due the following Thursday. And it has to do with the content that we talked about today. So the week previous. So it's the homework that's due next Thursday is the content we went on this week. And so then the content we talk about next week will be due on the following Thursday. So you have a fair amount of time. You have plenty of, I would recommend you chat with each other in the discussions. I saw everybody flying by right there. There's talk of setting up a Discord server or something like that. I am not going to admin. If you want to set up a Discord, you can. I'm setting up one for some of my other classes, but for this class, and you're welcome. If you want to invite me in there, I'm happy to chat on there. And same thing with Carter if he wants to join in on Discord. I just noticed that depending on how you want to set it up, or you could use any other kind of servicing like Slack or something like that if you wanted to as well. But I preferred that you use Canvas for the discussions because that's the official one. But I understand that something like Slack or Discord are a lot faster and a lot more convenient to actually communicate with each other on there. So I saw you guys passing around information with each other, but I think this is also a really good method to just network and communicate with each other. So I saw everybody talking last time, swapping handles, which I think is amazing. And I think that's great because obviously you are there's a lot more to you than what's going on in this class as a student. And so you're a musician, you're a producer, you're an engineer, you're an artist. And so I think like having that connection, and that's something that's sucking with this COVID thing, is that we're not having the student communication. So something like one of those like discussion channels are really good for that sort of thing. So I like Discord a lot. And if you guys want to set it up and invite me in on it, I would be happy to help out. And then you can use that for informal, well, we can talk about questions and homeworks and all that kind of stuff in there. But if you want to keep it private, that's fine too, and do your own thing with it. But I'm happy to hop in and help out and keep an eye on it. But I'm not going to admin the Discord for acoustics, at least for now. Maybe if you want me to, I can. But I'm probably, I don't know, I think it should be student run, just so that it's like more you guys doing your thing instead of me being like the overlord of this sort of stuff. So, but I'm happy to be a participant if you want me to help, if you want me to jump in on that. And same thing with Carter. So cool. All right. So what we're going to do today, we're digging right in, and we got into a little bit of it last class, just talking about the nature of sound and talking about where we're going with this. And so what we want to do is talk about how sound works and get an intuitive feel. Sound is one of those kind of interesting subjects, and I mentioned it last time in that it's kind of a tangible. It's not tangible in that you can touch it, but it's a real life physics thing. Like you can perceive it. It's part of our perception, and that's why I think it's neat, because acoustics is this kind of multidisciplinary thing, and it includes, as I've mentioned before, like physics and psychology and like psychoacoustics, architecture, music, art. It includes all these kind of things, kind of fold into this overarching thing of acoustics. But the thing is, what's neat about it is that it's like we can perceive it, we can interact with it. So one of the things that's like interesting for me is like when I walk into a room, for instance, when I walk into a space, I instantly kind of map out the room in terms of how it works and in terms of acoustics and how it is going to behave. And I look at the materials and I look at the dimensions and I look at all this kind of things, and I can understand kind of like, I can model the acoustics of a room kind of in my head out of the gates. But then also when I'm hearing sound and I'm watching a trumpet play, or I'm watching a singer sing, or I'm in a venue, I can sit there and I can understand what's going on with the sound waves. And I can almost, in my mind's eye, I can kind of visualize sound. And so that's what we're going to be working on today for a little bit, is this notion of how do we like getting an intuitive understanding. Like, I guess more than intuitive, not an intuitive, but a deeper understanding of how sound works, which will lead you to understand, like give you a deeper understanding of how like the physics goes on behind it. So let's talk about this a little bit. And so the classic way of starting to talk about how sound works in terms of physics is this notion of simple harmonic motion, SHM. So when we talk about simple harmonic motion, that's kind of like the root, or like that's one of the, I mean, you probably all, I mean, at some point have taken some sort of physics somewhere, maybe in high school, just took a general physics class, or maybe even a physics class here in college, or you're going to take one. But physics is one of those things that like when you take it, well, I don't know, when I took calculus, I was like, man, I love calculus, by the way. But like, I wasn't very good at it when I was in college, but I liked taking calculus. But it was one of those things that was kind of abstract. But it's only when you get into physics and you're like, oh man, then you start you apply all this calculus and you start to see how all this stuff works. Well, the same thing kind of happens in the physics world. We oftentimes talk about simple harmonic motion as kind of like one of the foundational like concepts in physics. But you're like, yeah, SHM, whatever. It is what it is. But then when you start to get into like sound and stuff, you're like, whoa, this is really cool. It actually like comes to life. So let's take a look at some SHM examples, like the classic physics examples, and then we're going to bring those into the audio realm. To do this, I'm going to use a couple different tools here. It's called FET. So I'm going to use the FET pendulum and the FET spring. And these are located in here. If we go into our modules, into our first week here, we have these simulations. And so I just created links of these things right here, mass and springs and a pendulum. So let's start with the mass and springs right here. And I click on this one and let's get into it. Actually, it just shows up right here. I want to show it up as its own page. It's embedded, but let's do it as its own page right here because I think it's pretty neat. So these are out of CU Boulder, the CU Boulder physics program. Let's do stretch, I guess. So what I have here, and if we were in class in a physical world, I'll bring in springs and masses and do this sort of thing in real life. But for right now, this is going to have to do. But the cool thing is with this one is that it works very, very well, and it allows us to, like you can play with this yourself. And so, in fact, you probably will. I think I'm going to ask you to play with these simulations yourself. You can go ahead and right now, if you want to go over and click on the link and start experimenting with these things, they're kind of neat. So what I'm going to do here is let's just grab a 100-gram weight and attach it to the spring here. And I'm going to turn off, do they have damping? Turn off, stretch it out and let this thing go. Oh, spring strength. Where's damping? They update these things quite often. Why don't I have spring strength? Let's try that. I don't know why there's no damping. Maybe I'm choosing the wrong one. Let's try one of the other ones. Maybe it's the lab one. Let's try the lab. There we go. Cool. Gravity. No, let's. Yes, I am recording it right now. Yes. So I'm recording it through ScreenFlow. I'm not recording it on. I'm not recording it through Zoom, and that's because in post, what I do is I actually do a little bit, so I can actually add in elements over the top of it and do like multi-editing kind of stuff. So yes, good question though. And so just to make that clear. So also under modules. So for like class 1, this is Tuesday's class. So this is course intro, and you will see your interface is going to look slightly different than mine. So that's the sign in thing. You don't have to do that one time. And now here's the video from last class. So everything is recorded. So thank you for the question. Cool. All right. So let's grab this 100-gram weight on here and let this thing go up and down. Sweet. So as we have this thing cruising up and down right here. So I'm going to see if I can grab this thing. There we go. Stop. See if I can find the middle point right here. Let's just do the resting position. Okay. Let's pull this off and drag it back on here. Cool. It's going to move a little bit right here, but I can't stop that thing. Right now, what happens with a spring, we've got something like this. We have this, what we call the spring strength. And in physics terms, you'd have your coefficient of your spring that determines how strong this thing is. And then we have our mass on it. So we have a mass, the classic mass on a spring right here. And if I'm doing my best, let me see if I can get it to move it to this position. I can't get it. I have to manually move it. So it's still wiggling there a little bit. But I don't know what it's determining as the middle point. Nope. Let's do it right here. Is that it? Nope. That. There we go. Pretty close. It's moving a little bit, but we can pretend that it's actually stopped. And so we say that right now it's at its equilibrium position. So we have the force of gravity pulling down, and we have the force of the spring pulling back up at this point right here. So we have a mass on a spring right here, and it's at what we call equilibrium. It's not moving. And so this green line right here is what we call its resting position, or its equilibrium position. And the reason we call it its equilibrium position is because the force of the gravity is exactly equal to the force of the spring. So they're pulling. So we have pulling in two opposite directions right there, and it's at rest. Now, what happens is if I stretch this thing beyond this, what's happening now is the force of the spring is greater than the force, the upward force of the spring is stronger than the downward force of the gravity. And when I let go of this thing, it's going to start going up and down. And as it just cruises up and down there, we're going to see that indeed it's going just back and forth right there. And what we see there is like when it gets up here, the string, when I go to the top right here, whoops. Oh, I want to pause it. Where's the pause button? Oh, there it is. Oh, there it is. Okay. At this point, when the spring has gone up, as we know, just intuitively, a spring is what we call a linear restoring force. So it's a linear force, meaning the farther I pull a spring apart, the harder it pulls back on it to get together. So, and then the same difference is if the spring becomes slack, if it becomes looser, it becomes less. It doesn't pull as hard. So the farther I stretch it, the harder it wants to pull back. And the same thing is the further it goes in, the less it wants to pull back. And again, the term for that is what we call a linear restoring force. It's got a linear force that it's pulling back here. So in the case of this one right here, as the spring has gotten shorter, as it gotten more slack, or it's less tension on it right here, the force of gravity is going to get stronger than the force of the spring. And so therefore, it's going to, and as the force gets larger and larger and larger relative to the force of the spring here, it's going to want to slow down and turn directions and go the opposite direction right there. So as I go up and up and up and up and up and up here, it hits its top point, and at that point, all of the there's a lot more force pulling down than there is pulling up. And so as I step through this thing, it's going to go down, 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 and then it gets stretched out beyond that. And now at this point, the stretch of the string is greater than the pull of the downward force of the earth, and it's going to want to pull it back up. And the result is it goes back and forth here, and it creates this kind of hypnotic thing. Well, truthfully, and that's why I had my slide. Remember, I had that little clock. You're getting very sleepy. We call that hypnotic. But if you do watch this, and if I slow this thing down, well, actually, I'll talk about that, like how we change the rate of this thing. But right now, it's going to go back and forth at a particular rate, and that rate that it's going back and forth is what we, of course, define as a frequency. It's how many times per second this is happening. So it's how many cycles. So when we have something that's cyclic, and we're going to talk a lot about that today, is when we have something that's definitely like cyclical, meaning it repeats itself over and over and over. Oh, Zachary, thank you for doing the Discord thing. Sorry, my chat is up on a separate window right here, so I have to look up to see it. So I apologize if I'm a little late to the Get Conversation game. I apologize. But what we have here is what we call something that's cyclical. It's repetitive. It's something that repeats itself over and over. And when we have something that repeats itself over and over, we can associate that with, in terms of time, how often it repeats itself. And that's what we call cycles per second, or hertz. So in this case, what we're looking at this thing is it's going up, down, and it's going down, up and down at a very constant rate. And in real life, I mean, we would have things like wind resistance that would actually slow this thing down. But because we have a simulation here, it's going to go for indefinite. It's just going to keep going and keep going and keep going. But the interesting thing here is I have two essential parts of a mass spring system. And this is just, you don't really need to take notes on this part. This is just kind of more trivia. Actually, in a lot of this stuff, you don't really need to be taking hardcore notes on this. This is more just like building an understanding of this stuff. So don't worry about like all the little details that I'm talking about right now. This is more just kind of like building a feel for this thing. But what we see here is that it has a particular rate associated with it. And that rate, the frequency that's determined is based off of what we call the spring constant and the mass here. So we have a mass spring system. And actually, we're going to be using this mass spring system, this concept, a lot more later in the class when we talk about things like Helmholtz resonators, or this is how speakers work. Like if you have a speaker that has a vented speaker, this is what. If you think about a speaker, like if you have studio monitors, or if you look around at most studio monitors, they have a hole in them, a port, and this spring right here is the air inside the speaker, and this mass right here is actually the mass sitting inside the port. So we can actually use this system here to model how speakers work, how rooms work, how a lot of different things work. So, but for now, we're going to kind of constrain this just as an intuitive model. But what the thing is that what we call the spring constant and the mass right here, those are the two things that define this. So if I were to grab this thing and let's see if I can grab it. Got it. And I'm going to stretch it much further. Actually, let me do this. I'm going to add some weight to this thing. Let's switch this out. I'm going to grab one so it's a little slower. So we can see when I grab the heavier weight, my equilibrium position moved further down. That's the resting position. So what we want to do is we want to figure out the rate of this thing. And if we want to calculate this thing out, actually, does this little tool work for us? Boom. That's not really that useful for it. And we could use it if we wanted to, but let's just try and figure the rate of this. Let's just do it intuitive. We're not going to do a mathematical one. Let's just build an intuitive one right here. It's going to clap, clap, clap. So I'm doing for every single cycle. So I'm going to catch it, or maybe I'll do it when the top of the weight passes through the green line here on going down. It's going to boom, 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 boom. So we see that as it goes down there, it's about 1 second, more or less. It's maybe a little bit faster than 1 second right there, or 1 hertz. We could say approximately. Now, what's interesting, if I grab this thing and I make this thing not go as far, if I make it just go a little bit up and down around this thing, is it going to go faster, slower, or stay the same? Just think about that for a second. So if I make it go less distance, is it going to go faster? Like is the frequency going to go faster, slower, or stay the same? Well, let's try it out. Boom, 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 boom. Holy crap, it's the same. Let's do it again. Let's go big. Boom, 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 boom. It stays exactly the same. Interesting. So what we can say here is that the I can't change the frequency. This system right here has one resonant. We call that, actually the term is called resonance. Has one resonant frequency. And we talk about things like a guitar string, or we could talk about things like the human voice or the room modes in a room. They have what we call resonant frequencies. It's resonant, and it has one. The resonant frequency means it oscillates at one particular frequency and no other. So and what we could call this is amplitude independent. So in other words, it doesn't matter if it's big or if it's tiny, it's amplitude independent. So in other words, it doesn't matter how loud or how quiet it is, the frequency stays the same. Interesting. So the point here, though, is that this mass spring system, the only way I can change the frequency of this, the two things I can change on this thing are, one, are the mass, or two, the spring constant or the spring strength right here. So if I grab this and I pull it off and I go to a tiny weight, boom, 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 it's moving faster. So it's it's moving faster right there. In that case, we can see that. So if I keep the spring the same and I make the system lighter, that it's going to be moving back and forth faster. And so we saw with the heavier weight, it's going to go lower, and with the lighter weight, it goes faster. So let me grab this again, and let's just pull off, and let's go back to like a known weight, or let's just go back to our big weight that we were using before again. So if I increase the spring constant here, so this kind of bodes with our intuition. If something's heavier, it's going to move slower. You know, we think about like an elephant, right? A lumbering elephant is going to move really slow. Or it looks like it's actually moving slow, but I mean, you could say that it's actually moving really fast. You guys remember Pacific Rim, the movie? I always thought that was interesting. I read an interesting article on, I'm not a big fan. That was Ang Lee that did that one, right? I'm not a huge Ang Lee fan, but Pacific Rim, if you remember the movie, it's what do they call the big mechs? What are those called again? Yeah, it's sci-fi. Help me out here. There's enough people in this class. What do they call them? Yeah, Jaegers. Yeah, they call them Jaegers. So this is, very classic Japanese kind of stuff where they have. Oh, it was Guillermo del Toro. That's right. Yes, you're right. It wasn't Ang Lee. Yes. Okay, that's you're right. Thank you for the correction there. It is Guillermo del Toro, which I think I like Guillermo del Toro's movies, but I don't love them. I think they're cool. It's the same thing. You could say something like Tim Burton or something like those, where they're interesting, but from a cinematic point of view, not my favorite. But in that movie, they talk about these Jaegers, these giant, huge robots, right? And they show them like running through like the ocean and the water and stuff. But I remember reading a thing talking about like if they were actually moving that fast in real life, given their size, their arms would be moving like faster than the speed of sound. Like they're just way too big. So even though it's like watching a jumbo jet fly through the air. You're like, man, that thing is moving so slow. How in the world can that be moving at 600 miles an hour? But yet it's like barely crawling. It's just because of the size and the distance that gives it that perspective of moving slow. But in the movies, they make them move fast, and you're like, there's no way you could actually have a robot, there's a lot of things that can't happen in that movie, but that can actually move that quick. So. Little sidestep there, but the idea here is that we see the correlation that with something that's big and heavy, it moves slower, and the same thing happens if I have something that's small and light, it's going to move faster. Well, and that we're going to build that into our intuition over the course of the semester and how that works. Sometimes it works to our favor, sometimes it works against us. But the other thing that we can do here is adjust the spring strength. So if I adjust the spring strength, it moves faster, and if I adjust to be looser, it's going to move slower. So those are the kind of two tools we have right there. So that's basically what we call mass on a spring. Now, if I'm going to go slow it down a little bit here, if I were to attach a pencil to this right here, and I were to drag that pencil along a piece of paper, it would create what we call a sine wave. So we call this sinusoidal motion. And if you look at it closely, it's not going like a triangle wave. It's not going constant rate up, constant rate down, constant rate up, constant rate down. As it gets to the top, it slows down and turns around, and it speeds up, and it goes to the bottom, slows down and speeds and goes up. So it's going slowest at the top and at the bottom, but it's going fastest when it's going through this point right here. And we can talk about it in terms of kinetic and potential energy, in terms of like physics, but we're not going to go there for today. I don't think it's fascinating from like a mathematical perspective, but I don't think we really need to talk about it. It's a little outside of the scope of this class, for at least for what we need to worry about. We will return to this when we talk about like absorption and how like absorbers work in rooms, because we will need to talk about this notion of kinetic and potential energy in terms of physics, but we're not going to do any math on it. We're just going to like understand what it is. And again, if you've had some experience with some physics in the past, that's sort of say that you understand this. So let's do this. Let's go back, and I want to do, instead of mass on a spring, let's just do real quickly. And I got to keep moving, keep things moving here. Is we have a pendulum right here, and let's do the pendulum one right here. And so we have the same kind of concept when we talk about pendulums. Let's do lab. Yeah, let's try the lab. I don't know what that is. So I've got a pendulum here. So a pendulum works the same way. Like, so if I've got a string right here and I've got a mass on a string and I let this thing swing back and forth, that we see that we have our equilibrium position here defined by the blue line, and then we have our displacement by this one right here. This notion of displacement. These blue lines, these are the maximum displacement right here. And we can see that it's doing the same thing. It's moving fastest through the blue line, and as it approaches this point right here, it slows down and then turns around. And we can see that we have now the force of gravity is going to be like, so it's basically instead of like the spring pulling it back and forth, it's going to be the weight of gravity pulling down on it as it moves through this arc. We can look at velocity right here, which is kind of interesting. So here's like, if the green line, it shows how the green line is velocity, how fast it's moving. So it slows down, and velocity also determines direction. We'll talk a little bit more about this. Oh, do they have an energy graph? Cool. So here's kinetic energy, here's potential energy. And the total energy stays the same. We don't need to talk more about conservation energy and all that stuff. Although I do think that's really fun and really cool. But the thing is, the same thing was with this. If I hit stop, and the same thing happens. If I let this thing go slow, or if I let this thing displace small, it still has boom, boom, boom. And then if I go big, boom, boom, boom. So once again, the frequency stays the same. It can't change. This system is a resonant system, has one frequency it resonates at. So it has nothing to do with the amplitude. I mean, if I go way up here, like in real world, if I start like going way outside of it, if I stretch a spring too far, that it gets wacky. Like things go outside of this normal linear range, then things can happen. But for like normal stuff, it has a constant rate right there. And so that's an important concept to understand, is that it has this mass spring system. So that we could call it a mass spring here. It's a pendulum, but we can still think the restoring forces are pretty much the same thing there. Okay, I want to get moving on here because that's a little further. But how do we apply this to this notion of sound? Okay, let's see. Oh, yeah, okay, we have one more. Let's go back here. And what if we were to turn this into rotational information? So if I were to take, and this is one of my favorite demos to do, is if I take a wheel, like I take a circle that I have right here, and I attach a bead to it, or attach a post to it, and if I were to rotate this thing and look at it on its front and back, it would draw what we call a sine wave, or like this is the cosine wave is out of phase with it. But we can look at this and let's see if I can get this thing to go. So what we can see here is that rotational information also correlates to sine waves. So we see that this notion, so we have a mass spring, a pendulum, and circular motion all result in this, what we call a sinusoidal motion, which is really interesting. It's one of these kind of like underpinnings of nature, of how things move. And so when we start to get into this, and so when we see that we have sine waves, that we have a sine wave, and whether it be from a mass on a spring, a pendulum, or a rotating system, they create these sine waves right here. And what we could say is, instead of taking a circular circle and creating a sine wave from it, we could also say that we could take a sine wave and rotate something from this. And we could see this little yellow this little yellow diagram right here, and that's showing theta, which is what we call angle. So when we talk about, we can correlate our sinusoidal motion to angles, which is interesting. So circular motion and sine waves are actually correlated to one another, and we call that phase. So we can define this right here, this notion as what we call phase. And we kind of have this notion of this. We probably all have an idea of like when, well, especially because in AP1, you're talking about this, that when things are in phase and when things are out of phase. But of course, in phase means they're exactly the same, and out of phase means they're exactly opposite of one another. But there's a whole slew of angles between in phase and out of phase. So we'll talk more about that stuff later, especially when we talk about like comb filtering and some of these other concepts. But for right now, I just want to bake in this notion of that we have this circular motion correlates to angles. And which we can correlate to sine waves and also cosine waves, but we mostly talk about this in terms of sine waves, at least for our discussion right here. So let's talk about. So then let's take a let's apply this. Back to. I guess I want to have that open, and I want to go back to the wave here. Let's take a look at this one last example of this, and. Oh no, we're gonna talk about this one coming up. My bad. Sorry, I'm going a little out of order here. So let's talk about this notion of sound and medium. So that was just basically what we're doing is we're developing a model. I want to get you this intuitive understanding of sinusoidal motion, and now let's talking about sound, and then we're going to marry those two concepts together with one another. So, we talked about last class that you have to have three things. Essentially, you have to have three things for sound to occur. You need to have a disturbance and a medium, or you need to have a disturbance, a medium, and a listener. So the medium is something that's really important. And so you can't have sound that actually, if there's no medium, sound does not propagate. And the classic demo for this thing is called like a bell in a jar. And this is really fun to do in real life. I've got the demo at school, and it's bizarre to experience this thing. But basically, what you do is you have what we call a bell jar here, and we have a pump. And what this pump is going to do is it's going to suck out all of the air out of this thing. And you've got this it's like a bell that dings like a. Well, actually, let's just watch it. I have a YouTube version of this thing. Oops, I want to go back and let's do the YouTube of this thing. It's not as good as watching it in real life, but we have to make do, right? Pretty quick. All right, I'm gonna go ahead and stop it. Yeah, you get the idea. Thank you for that link right there. Yeah, I can post it. Yeah, I guess you already posted it right there. If you want to check that out on your own time, it's cool. It's the problem with this one is like it's not a very good one because I like when you can physically see the bell moving because you can see that it's actually happening. He's just using a little alarm that's like an electronic alarm, so it's not as good. I don't think this one is as good as an experiment, but it's very bizarre to see this thing happening in real life. It's fascinating to see it do its thing. So, but you kind of get the idea, and the reason, of course, like we had mentioned before, in space no one can hear a scream, right? Because without any medium, there's no propagation. So what we want to do is we want to talk about a little bit about this idea of the medium and particle motion and how sound propagates through sound right there. I'm sorry, that was a weak demonstration. I was like, in my head, I whipped that one up, I pulled that together. I was like, oh, this will be cool to show as a demo. But yeah, of course, this is super lag. I think for me, yeah, Bryn, I totally right. It does feel fake, right? Like it is weird. It feels like a magic trick. Like it doesn't feel right. So, someday when we get back on campus, hit me up and we'll do like a little like demo. But you can watch them all. But like you can watch them all the time on YouTube and stuff like that. But there's nothing like seeing it in real life. It is a bizarre experience. It is pretty crazy. So, let's talk about this idea of particle motion. So, how sound works and how this idea of simple harmonic motion and elasticity pull back into this notion of sound and simple harmonic motion. When we talk about, does anybody remember this ad? Does anybody I guess what's wrong with this? What do you think? What do you think is wrong with this? Oh, you said, what about particle accelerators? Yeah, that's basically, yeah, when they're moving like the Large Hadron Collider and stuff, when they're moving the particle around like really, 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 really fast. The particles, they're actually like pushed through using magnets and energy. So they're actually like putting those on a course. And that's actually kind of like relates to what we're talking about here. But sound is a little different than a particle. So sound is an energy, and that's what we're building up this notion that sound is an energy, and it passes through this medium. But, well, let's talk about this picture for a minute. But there's some caveats there. I always love this. Growing up, I remember seeing this ad. I mean, this is a little bit older than me, but I remember this ad. Actually, if anybody remembers that, yeah. Yeah, rad. I like the idea of what they're talking about here, right? So this is by by the company Maxell, who makes analog tape back in the day. I don't even know what they're making today. They're probably making media, but they used to make cassette tapes, and they were trying to show that like the sound is just gonna blow you away, right? That it's like it looks like it's blowing like wind. This dude is sitting in front of the speaker here, and actually, does anybody recognize that chair? That chair is badass. I have this chair next door, like in my house. This is a famous design chair. I have a white version of this one, but what I'm curious about is how they did the glass with the water. I wonder if that water is fake, if that's like urethane, and they just balanced it there. But very cool, nonetheless. It's a cool imagery of like getting blasted, like you guys are talking about. I mean, it's like it implies this like just blast of energy, but this is not how sound works, right? So the thing to note here is that the sound is passing through the medium, but the medium is not moving. I'm going to say that a number of times. The sound passes through the medium, but the medium itself does not move. And to prove this, well, let's just take a look at this. Let's use a little example here. Got me a little candle. And let's light this thing up. Come on. Brand new candle, so it's not lighting very good. Give it a second to do the flame. Can you see the flame? Hopefully you can kind of see it. Yeah. Cool. I'll move out of the way so you can see it better. All right. So a flame is a really good indicator of air motion, right? If I blow on it, just barely have to blow on this thing, and it'll move quite a bit. Like if I'm just barely, and I'm talking about barely blowing, we're seeing the flame motion right there. But if I sing at the thing, doesn't work. It doesn't move. I'm right on that flame, and it's not really doing anything. So so what we're seeing here is it flies exactly in the face of what we're doing in this video, or in what we see on the screen there. So what this is implying here is that the energy is moving through the medium, but the medium itself is not moving. Cool. So let's put this, yeah, wrong, but cool looking, right? So what we want to do is let's take a look at this and how does this like tie into this notion of simple harmonic motion. So what I'm going to do here is I'm going to go back over to this last one right here. New window. Cool. Let's do sound. And what I've got here, so I've got a medium. So this medium here is going to be gray. And what I'm going to do is I'm going to let this thing go into sinusoidal motion. So I have a speaker, and the speaker is going to push and pull on the air molecules. And what we have here is, if we think about air, before I hit play, let's talk about what air is. So air is a bunch of different molecules that are like try to be equilibrium distance from each other. So in a silent room like this, and this we'll call this like a silent room, all the molecules will separate from each other. In this case, we'll define this as the air molecules as being white. So the closer they are, the whiter they're going to get, and the farther apart they are, the darker they're going to get. It's going to cause like more space. And we call those compression and rarefactions. And as we go through on this, if I squish air together, well, if I don't do anything, the air wants to distribute itself around the room equally. If we think about something like a glass of water, if I pour water into a clear glass, it's going to distribute itself amongst the glass equally. I mean, there's going to be, technically it's going to be a little more dense at the bottom than it is at the top, but we could say that from a visual aspect, the water fills the whole space, and it wants to. So you can't make water only fill half the glass without putting up a partition or something like that, without something else happening. Well, the same thing happens with air. If I put a bunch of air molecules, a bunch of molecules in a space, they're gonna distribute themselves equally. And just like the water at the bottom, they're gonna be a little more dense than they are at the top. Like if we think about it in terms of the atmosphere. Down here on the surface of the Earth, the air is much more dense than if we go higher up into the atmosphere. But for like a small, all intensive purposes, we're just going to call this that it's going to be equally distributed right here. So what happens is I'm going to be able to, like, the air molecules like to equally distribute themselves, but because they're far enough apart from each other, they have the ability to squish closer together, and I can stretch them further apart. They're squishy. Like, right, and we know that air is squishy because like you can stick it inside of like a scuba tank or like a compressor. Like you can squish air together. And so we can the air ability has the ability to squish up, but it also has the ability to pull apart. Like we saw in the video, we can put it under a vacuum and it's going to spread itself apart. So air is squishy. It's got this like elasticity. Oh, wait a minute. Weren't we just talking about something with elasticity like a spring? Well, what we can say is that air molecules, they actually wiggle back and forth, just like in the same way that the springs do. They don't actually, the air itself doesn't resonate in the same way, but that concept of that we have this restoring force. You can think about air as having molecules with a bunch of springs attached all over them. Like, and I've seen diagrams of this where you have particles and they're attached to springs, but all these springs are attached to the other springs and it becomes a big hairy mess to draw. But the idea is that they're just like, you can have some pulling back and forth there and squishiness right there. So, so what I'm going to do here is I'm going to hit play on this thing. Where's my play button? Is that it? There it is. Okay. So what we have here is it's pushing and pulling on it. So as it pushes, pulls, pushes, pulls, pushes, and whenever it pushes on it, it's gonna squish them together, and it becomes a white version of it. And then whenever it pulls, it's gonna be called what we call a rarefaction, and it's gonna be a lower air pressure. So what ends up happening? Let's see. Do I have where's my pressure monitor here? Let's just look at one of these. I only want to look at one right now, and we can look at this in terms of the air pressure. So the air pressure right here it's above ambient. So if I hit stop, or how do I hit stop? Oh yeah, it was stop. So that basically this is what we call ambient air pressure. And when it goes above ambient air pressure, it's a compression. When it goes below, it's we call rarefaction. I'll say that a few more times as we go through here, but we can see that it goes up and through there. Now, what happens if so this is going at a constant rate right here. Remember, this is moving at a constant rate, but I have the ability to change the frequency. So if I change this frequency, just like with a mass spring system, if I were able to change them, if I wanted to change something, if I change the frequency of this thing, if I bump it up, Let's look at how fast the waves are propagating through the medium right there. It's a higher frequency, but the speed at which these are moving is exactly the same. This is kind of this is one of the little more mind-blowing things. Well, let's just hit the nail on the head and let's talk about it. That the wave velocity is independent of the medium. So in other words, or is independent of the frequencies. Let me say that again. That the wave velocity is independent of the frequency. So just like with the mass spring system, I can't change the speed. I can't change the rate at which it travels. I can change the frequency, but it doesn't change any faster. And this is a good thing, right? Because intuition would probably tell us that if I increase the frequency, it's going to move faster. And if I decrease the frequency, it's going to move slower. But that's not the case. And again, that's a good thing, because say you were listening to some music. If you were listening to music coming out of your speakers and the high frequencies travel through the air faster than the low frequencies, it'd be a garbled mess. You wouldn't be able to understand anything. So what happens is all sound travels the same speed through the medium. It's independent of the rate. There's some caveats there, but we'll get to that later. But but all frequencies travel through the medium at the same rate. That's really important. All right, I'm going to say some more stuff about that later, but nope, that's actually it's still traveling the same speed, but that's because your two objects are moving at different rates. And I used to spend a lot more time in my other class talking about Doppler. We're really not going to talk about it too much in this class, but that if you're moving it away, it just stretches the wavelength out, but it's still traveling at the same speed towards you. The caveat that I'm talking about is either one, density, because I think somebody mentioned it up there, is that if you change the density of of sound, they change the density of it, it moves faster. So sound moves faster in water because it's a lot more dense. Or if you change the temperature. So the temperature changes the density of sound, and also it changes the rate at which it moves through there. And we're going to talk about that here in just a couple minutes. But the idea is that if it gets warmer, that the waves travel faster, and if it gets colder, the waves travel slower. And that's because the air molecules are wiggling, and if they're colder, they move. They don't propagate the energy as fast through the medium. But density and temperature do affect the wave velocity. But so those are when I say like you're saying edge cases, those edge cases are going to be they're not even like that far edgy. They're just not part of the equation yet. I haven't added those into the equation. I'm simplified the model right now, and we're going to add more complexity to the model here in a minute. So let's look at this right here. If I change this thing to particles, let's stop this for a moment. And I'm going to switch this over to particles so we can see them a little bit easier. In this case, what we're looking at is the air molecules. We'll pretend these air molecules, they're hitting their equilibrium position right here. And as they start to settle down, so, and in real world, they actually always do continue wiggling right there. That's what heat is. Heat is the vibrational energy of this. So if they're hot, they're vibrating really fast. And if they're cold, they're vibrating really slow. So they're always kind of in this state of just trying to equalize, and they're trying to like equalize with each other. But we see that for the most part, the medium is not moving. It's not shifting altogether. It's not like wind. But we can see that because of the red dots right there. And so the red dots are there just so we have a reference. It's easier for us to key in on what's happening there. So now what I'm going to do is I'm going to press play, and I'm going to see the same thing happen. I'm going to move to a mid frequency here and hit go. And we see the compression wave right here, and we see the rarefaction wave in the middle of that. And we can see that the waves are propagating through the medium. So the medium is the waves are propagating through here, but we can also see that the medium itself is not moving. It's moving back and forth, but overall it's not moving. So this disproves that Maxell that we were looking at right there. And again, it'd be awesome. Like it does move back and forth, and you can perceive this, right? Like if you walk in front of a gigantic subwoofer, at least for me, because I have pretty hairy legs, I can feel my leg hairs moving back and forth right there. But it's not a wind. It's a vibrational energy. It's not wind. So I can feel my leg hairs, the air molecules are moving back and forth fast enough that it actually makes my hair move back and forth. And like if you were to set this candle up in front of that, it'd be moving so fast you couldn't really see it, but the candle itself would be vibrating back and forth a little bit. But usually you can't see it. Because, I mean, even something as low as, say, 30 or 40, 50 hertz, which is really low on the spectrum, is actually kind of hard to perceive for our eyes. Our eyes only have a frame rate of about, well, we have a frame rate of about 30 frames per second, or 30 hertz, you could say. So um, anything above 30 hertz, we wouldn't really be, it would look like, it would smear it. So it would look kind of like a blurred, it would look like a blurred, candle, not an actual moving back and forth right there. So, but we see so the important thing to note here is that the medium is, the wave is moving through the medium, but the medium itself is not moving. It's vibrating, but it's not moving. It's not like wind. So, but wind, if I had a crosswind on this thing, it would be doing some weird stuff, and wind can cause some weird stuff. If you're at a show and like at an outdoor concert and you have a really strong gust, not even strong constant wind, but gusts of wind, the sound does change and you can hear it. It will change the way that it sounds. But it's still going to be passing, even though if it's traveling down there, it's still going to be passing through the wind at a constant rate through that wind. So interesting. Cool. Yeah. So, so like I just saw your stuff go over there. Like I say, maybe a medium, a denser medium is a stronger spring. That, yes, and also that the distance, the more dense they are, the closer they are together. So they pass the information from one molecule to the other one a lot quicker. Whereas this one, it takes more time for it to squish up and push that one, and then pull back and pull on that one. Whereas if they're closer together, that energy is transferred from air molecule to air molecule a lot faster. The springs are a lot closer together, so to speak. And so they're like stiffer springs too. So good questions. Yeah, and so we're going to talk about that when we start talking about constructive and destructive interference and like reflections. So we create like areas of velocity and nodes and antinodes, where basically if you have a speaker pointing down a piece of plexiglass and you have those little beads floating in there or going sideways, you can create what we call standing waves. And basically it's where the wave is like reflecting, and it feeds back on itself in some areas and cancels itself out in other areas. So the little foamy balls, those styrofoam balls, are going to collect in the nodes where there's not a lot of motion right there. It's like it wants to settle where there's not a lot of motion, just because there's momentum. It wants to settle where there's not as much energy, like an energy null, and so they'll actually point in there. So that's not quite exactly the answer that I think you're probably looking for there, but yes, we will talk about that. And I don't want to just not talk about that now, but we need to keep moving, because I think it's really important that we kind of get through this kind of fundamental concepts here. There's a couple things, and then if we have time, we'll come back to that. So I'm sorry if I didn't quite all the way answer that, but we will get to that further. I think probably in a couple weeks we're gonna really dig into that concept quite a bit. So that FET thing right there, it's also as a link, and I strongly encourage you to I think this mass spring ones are okay to play with, but the sound one I think is really good if you want to play with that thing. Hook it, it runs in the browser, play with it. It's pretty neat. And it will help kind of like build in this intuition of how sound propagates through the medium. So here's what we're talking about. This is how we correlate back to simple harmonic motion back to waves. So basically, we can think about this particle right here, and we were doing it up and down before with the mass spring, but we can also think about it as springs against its neighbor. And so we have a particle right here. So the particle is going to move back and forth and back and forth. And it's going to, if I were to map that out and drag a piece of paper on it, just like I was talking about with a pen, it's going to draw out a sine wave right there, which is really cool. So that particle is moving back and forth in a sinusoidal motion. It can move back and forth faster and move back and forth slower. The velocity is of the wave is the same, but this frequency can actually change. And the further it goes, actually, let me pull that back. Let me pull up my FET back up again right here. Let me go back to this one. And if I go to amplitude, if I go to a low amplitude right here, in other words, the speaker is moving back and forth just a little bit, we can still see it passing through here. It's let's move it up a little bit. It's harder to see. That we can see the displacement right here. If I look at this red one right here, it's moving back and forth and back and forth. And it's jiggling, but it's moving back and forth in a sinusoidal motion. And if I stop, it wants to hit its equilibrium position, its resting position right there. But if I go really loud, in other words, if I crank up the amplitude right here, we watch the same one right here. It's moving back and forth much farther. So it's moving back and forth in the air really far. And in real world, it's tiny, but in this visualization, it's moving back and forth, back and forth, and back and forth. So the idea here is that this displacement right here, the air molecule displacement, correlates to amplitude, which we can then correlate to also how loud it is. So the farther the air molecule displaces means the harder and like it's pushing and pulling on our eardrum, which we correlate to being loud. So a small displacement is quiet, a large displacement is loud. Cool. So the density will let's see. So the density, like, it's what we say is that the amplitude will still move back and forth. If you change mediums, which we'll talk about coming up later a little bit, not today, but when you change mediums, the amplitude will probably change significantly. But if I were to, like, say in a media, if I were in a medium and I like the displacement of sound in air and the displacement of sound in water, it's going to be a much smaller displacement probably in water. I guess I don't have a hard answer without doing equations on that one. But yes, probably yes. But it's got a stronger restoring force, so it will maintain. If you can get that thing excited, it will maintain that amplitude. So it's harder to, like, it's probably harder to get it started, but it's like, but it will carry. Yes. And in my models right now, on all the models I'm talking about right now, we're not talking about friction and loss and all that kind of stuff. Like and because in real world, like, that air moving back and forth does actually create friction and it does slow down. So if you're farther away from something, not just because you're farther away from it, but it will lose its energy because air just absorbs energy by itself. It loses it to heat. But I think that once you get it excited, like in solids, like you think about like like train tracks and a train coming down a train tracks, you can hear the sound coming through the train tracks really well from very far away because that, like, steel is a really, really good conductor of that energy of those not air molecules, of those steel molecules moving back and forth. They don't move very good, but once you get them going, they maintain that amplitude. So yeah, I think, I don't want to get bogged down in well, I don't even have the equations in front of me. I used to have the equation. I do have the equations somewhere in some notes, but I don't have them in front of me, and I don't want to say the wrong thing. That's really what it's coming down to. So, but those are good questions. Thank you. So thanks. Yes. And feel free to interrupt me anytime with this stuff. Okay. So we've got this idea of waves, and those waves can come up in different forms. What we're going to say is that, like I don't have it pulled up as a slide, but sound is an energy that passes through a medium. We've kind of defined that loosely at this point, but when sound is an energy, and that energy is like, that energy shows up in the terms of displacement. So, like, right, the energy is, it passes through the medium. It's a disturbance. That disturbance means I'm going to displace this molecule from its equilibrium position. And to do that takes energy. And that energy is going to get passed on to its neighbors. That displacement energy gets passed on to its neighbors and passes out. And one of the weirder things about that is that we have what we call, again, the compression and the rarefaction. A compression is where we squish the air molecules up and they pass that energy all the way to their neighbors and it passes out. The less intuitive one is when I suck on it, like if I have the speaker and it sucks away, that it still propagates out. Like, that's the less intuitive one. If I squish on it, it pushes out. That makes sense. But if I pull on it, it also sends the vacuum out, which is strange to think about. So it sends less, and we could see that happening in that thing where basically all the squished molecules are going out, but we also see the rarefied molecules being propagated through the medium. And so it's a little bit strange to think about that, but they're actually passing through that. But we can think about this, that there's two different kinds of, we're going to focus on essentially two different kinds of waves right here. Well, let's just talk about this one right here, transverse wave. And I should have set up my demo for this. Oh, well, I guess I have something that works right here. Look at that. I happen to have some little bungee cord sitting on my desk right here. So we have two. We're going to talk about, well, we'll talk about three, but I really want to like focus on two. So we have transverse waves and we have what are called longitudinal waves. So a transverse wave is a wave where the particle motion is perpendicular to the wave propagation. That's this. It's hard to see it, and I'm holding up a little bungee cord right here. But it's, if I were to take up a long piece of string, and like that's why I use the picture of a guitar string right here. In fact, like this is a snapshot, a high speed snapshot of a guitar string, and we can actually see the waves on a string right here. So a transverse, like a good example of a transverse wave is a wave on a string. And that's where we can, and if it's like a loose enough one where you can actually see the wave propagate, you can see that the wave is going, the wave motion is up and down, but the wave propagation is along the string. So we can see that this is the wave, this is the wave motion, the wave is going to be traveling down the string, but it's moving up and down. And you're like, well, yeah, that's just how waves work. Yes. But it's moving. So, but the idea here is that particle motion is perpendicular to wave propagation. So I said particle motion, or I also say wave motion. So you can use particle and wave interchangeably in this case right here. So transverse wave, for particle motion is perpendicular to the wave propagation. I'll go to the next one. And we'll come back to this because you're like, I think I get it. You may be thinking about that, but it'll come clearer as we discuss the other one and come back to this one. The other one is what we call a longitudinal wave. So where particle motion is parallel to the wave propagation. So the classic example for this is using like a spring or a slinky. So I accidentally left. I was going to do that for class today, but I left my slinky on campus. I got up this morning, was looking through my notes. I'm like, my slinky's on campus. But if I do a slinky and I pop if I have stretched out slinky and I pop it, you can see the wave traveling back and forth, but the slinky itself isn't moving up and down. You can make it move up and down, but that's not what I'm talking about. We're talking about popping a spring. It's a compression wave. So longitudinal waves are compression waves. That's what we're talking about right there. So in other words, and also air, like sound in air is a longitudinal wave because what it's doing is it's pushing on its neighbor and pushing on its neighbor and pushing and pulling on its neighbor. So the wave is traveling in this direction as well as the wave motion. So the wave motion is moving back and forth like this. The particles are moving back and forth like this, and the wave motion is traveling down down a direction of we'll say a direction. Whereas this one, a transverse, is where it's perpendicular. So a string is moving up and down, but the wave motion is up and down, but the wave propagation is down a string. So a wave on a string is a transverse wave. An air sound in air is a longitudinal wave. There's other like examples of this, but we can think about I guess those are the two kind of classic examples, and I don't want to dwell on those for too long, but those are the two kind of like the main principal ones that we tend to talk about there. So we have, again, longitudinal waves are where it's parallel and or what we call compression waves. So if you want to think about it, if you're taking notes, you don't really need to take notes, but if you want to take notes, my goal is that in this class, you shouldn't have to take notes. If you read the book and you watch my lecture and you read the book, you likely won't have to take too many notes. So and I'm giving you all the slides. The slides are posted so that I think I posted those up. Yeah, if I didn't post them, I will. I'm sorry if I didn't get those. I just realized I may not have posted those, but I will always post the notes. So that basically a combination of like reading, listening, and watching. I don't want you like furiously taking notes. This isn't a note taking kind of course. I want you listening to me and watching, and I want you thinking about this stuff. So but if you were to write something down, you could, or just log it in your brain. You say longitudinal waves are sound waves or compression waves. So longitudinal equals compression. It's not always, there are more longitudinal waves than sound in air, like earthquakes and like tsunamis. Those are compression waves. So like where like the tectonic plates shifts and it shoves on the earth next to it, and these travel, and they travel very, 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 very fast. But like transverse waves are waves that move up and down. And again, we can think about this one as waves on a string. That's the one. Here we go. Here's how you remember it. Remember Merkel doing his wave. This is a transverse wave. Yeah, I did breakdancing when I was a kid. I'm sure you guys are way better at it than I am. But that's how you remember it. Okay, I'll burn this in your brain. Transverse. 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 I'll give you something like log on to remember. A wave is, yes, correct. A wave is not a particle. A wave is made up of particles. So particle motion. So particle motion is the particle itself moving back and forth. And so you could also say wave. Wave motion and particle. I'm using wave and wave and particle are interchangeable, but a wave is made up of particles. And then the last one we have here is circular waves. So where the particle motion is circular, and this is like water waves. So we can witness this one if I go back out of this, and I have the waves intro right here. If I were to, I think I have the ability in here to show it. Let's see, side view. To show in particles. Yeah, I think I can look at it here with this one. I don't know. I haven't used this one for a while. They're not going to show the particles here. But if I were to look at it, basically, if we're talking about, like, you can kind of think of like a water wave almost as a transverse wave. It looks like it looks like a transverse wave, but really what's happening is the water particles are moving in circular fashion. And if you've ever been like in the ocean in a wave, you can, as the wave goes by, you can feel it. Like you feel yourself get, like, if it's a pretty good sized wave, you can feel yourself going up and down, but also getting pulled back and forth. And so when you're in the ocean, you can feel yourself. You're not just going up and down. To a distant observer, it looks like you're going up and down, and it looks like the waves are just passing by you. But really, if you can feel it, like, you can feel yourself going up and down and back and forth. You can feel that circular motion right there. But I don't really want to spend too much time on that one right there. Like the water one, that's kind of like, I won't say that's an edge case, but that's just like, that's not really relevant to like our discussion in terms of sound. We want to focus on sound. But I do think that when we talk about transverse and longitudinal waves, it's interesting when you think about, like, say, like a guitar or instruments. When we talk about deconstructing of musical instruments, they're taking transverse waves and converting those into longitudinal waves. So a transverse wave is a wave on a string that the body of the face of a guitar, basically the bridge gets pulled back and forth, and the bridge of a guitar pulls back and forth, and it starts to act like a speaker, and it creates a compression or rarefaction wave. So it's interesting to think about like an acoustic guitar or a violin or any kind of stringed instrument. Stringed instruments take these transverse waves and they turn them into longitudinal waves, which is kind of cool. It's a kind of a little trippy and heady way of thinking about that. Cool. Okay. So and we saw this a little bit, and I want to come back to this notion of compression and rarefactions. So compression is where we see that there is the air molecules squished together, and rarefaction is where they're pulled apart. So we can still see that this is probably, so in this rate we have direction of wave travel to the right. So this is pulled directly from the book. And by the way, if you haven't gotten the book, please get on it. Get on the book and start reading it. It's a solid read. But we can see that this is a compression, this is a rarefaction, this is a compression, rarefaction. And like, basically they're trying to show that this is a snapshot in time. This is really hard to show in books. So this is like, this compression wave right here is this compression wave right here. So we can see that it's kind of traveling to the right. So in other words, it's traveling in this direction. This is only a snapshot in time over two of them, but that we see it's actually traveling over here. So that's essentially how that's how the energy is propagated through the medium. The medium being, of course, these little air molecules right here, and they're squished up and they're pulled apart. But the energy is passing through the medium, but the medium itself is not moving. But what we want to do is, like, for us to represent that in terms of a drawing, or how do we do that? This is a very difficult thing to draw. So what we're going to do is, like, we have what we would call traditionally like a wave on a string, and we have a transverse wave and a longitudinal wave right here. But this one is very easy to see. We can see that this is displaced up to the top. This is displaced down, displaced up, displaced down. But here we can see that this is a compression, this is a rarefaction, compression, and rarefaction. What we're going to do is we're going to make this longitudinal wave look like a transverse wave. And this is, my friends, is what we're used to seeing a lot of the time. So let's look at this concept here, visualizing sounds. What I'm going to do is I'm going to go over to my Finder. Let's just pull up Ableton for a second. I'm just going to use this I should have probably had Wavelab pulled up, but just because I feel like it, I'm using Ableton. This stuff, like everything I'm talking about is platform agnostic. It doesn't matter. It's just science. So Ableton works as well as Wavelab, which works as well as Pro Tools. But what I'm going to do is I'm going to bring in, let's just grab let's grab a clip. I'll just grab a sample. Let's do something like, I want to find something analog-ish. Let's do bongo. That'll work. Actually, I'm going to move that to here. Let's take a look at this bongo here. Where's my stretcher? No. There we go. Let's make this big. Enough warp. And, oops, no, I don't want to play. Let's just zoom in on this thing. What we see here is our classic waveform. So if you're working in Pro Tools or we're working in any DAW, when we work with digital audio, we're used to seeing these things, what we call waveforms. And to our eye, we might consider this to look like a transverse wave. But what it's actually representing is a compression wave. It's actually like, this is actually representing a longitudinal wave. And what we could say here is that what we're doing is we're taking a microphone in this case. Well, this could be synthesized. This is a bongo, so it's actually probably recorded. So we took a microphone, and we have a microphone, and as that sound wave hits that microphone, and we'll talk about like a dynamic microphone, like a SM58, for instance. And as that 58 moves back and forth, it's got a permanent magnet and a coil of wires, and it basically, by that thing moving back and forth, it induces a current in one direction, a current in the other. And that current, because a computer can't actually record sound directly. It doesn't understand, computers can't like understand sound. What we have to do is we have to transduce it into electricity, because computers can understand electricity. They can't really understand sound directly. So what we do is we take a microphone, and a microphone is a transducer. It changes the energy from one form to the other. We're going to spend a lot more time talking about that later in the semester. But basically, it turns into energy, and that energy we can map out in terms of voltage. So what we can say here is that we could say that this is higher voltage and this is lower voltage. Higher voltage, lower voltage. We could actually call this negative voltage and call this positive voltage if it's above and below the zero line right here. But what that correlates to is that this is a compression wave, this is a rarefaction. This is a compression wave, this is a rarefaction. And a compression wave, and a rarefaction, compression, and rarefaction. So what we see on the screen looks like a transverse wave, but it's actually representing a longitudinal wave. And that's that's like something that may have not ever really considered before. It's really cool to think about this, that this is actually representing the pushing and pulling of airwaves of sound in air. So, because most of us, when we're working with sound and editing and creating music and beats and all that kind of stuff, we just kind of cruise along and we just see this stuff and we understand it kind of intuitively. But I think it's worth stopping and taking a step back and going, wow, that's really cool. That's really interesting that actually represents the sound waves in air. So yeah, I think this is really cool. I'm going to keep going, but like we got to stop now because it's actually 12:15. I could go on to this stuff all day. I love this stuff. All right, so what I'm going to do here is I'm going to go back here and let's exit out of here. I had a couple of things that I wanted to get to, but we'll have to get to those next class because I just didn't quite have the time to get to it. I want to talk about like the speed of sound and talk a little bit more about the nature of sound here. So let's get out of screen share. And with that, my friends, we're going to head into the weekend. So the homework is posted. I didn't get to all the stuff. There's a couple of things that I need to get on to next week that are like included in the homework. But what I want you to do, your task for over the weekend is to get the book and read through chapter 1. If you haven't already, get on it. It's a great book. Yeah, like I would recommend, well, I don't know if you want to get the Kindle or the physical version of it, but it's Kindle. It's super simple. You can just grab it and go for it. So without anything else, I'm going to stick around. I'm going to go ahead and stop the recording right now, but I'm going to stick around for questions if anybody has anything. But hit me up. I have office hours from now till my next class. But yeah.